Okay, 512. So continuing our exponential functions. Can two transformations be equivalent? So looking at transformations of exponentials and looking that could two of them then potentially get you the same solution with exponentials? So let's jump right in here. 512. Question problem 12. Can two different transformations give the same result? So explore this, consider the function. So we have this function 5 times 2, and that's raised to the 3x minus 2. Okay, so can this equation also be written in the form y equals a times b to the x? That's standard form. So let's work and see if we can determine this, right? So what happens here? Well, the first thing almost everybody sees is, well, let's just distribute the 3, right? So sure, I mean, we can go ahead and do that. So 5 times 2 raised to the 3x minus 6. Okay, then what happens, right? Like we have to understand our exponent rules. This is 2 to the 3x times 2 to the negative 6, right? Because we add exponents when we have the same base. Okay, well, that can help us clean this up because this is then 5 times 2 to the 3x over 2 to the 6th, right? We take that negative to the bottom. Okay, so let's continue to clean that up. So this is 5 times 2 to the 3x over 2 to the 6th is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. So we have 64 down there, right? So now we have 5 times 2 to the third, then raised to the x. So we got to understand that 3 and x are multiplied. So in order to do that, it's just power to a power rule. So then we can go 2 to the third, which is 8, right? So 5 times 8 to the x over 64. Right? And then to make this that a times b, this would be 5 over 64 times 8 to the x, right? So that's that a times b to the x. Okay. Um, okay, so continuing this, let's work with some exponential functions and some properties of those. So it says, first thing here on 13 says you have 3 to the x, and it says to graph that, right? So if we graph that 3 to the x, right, you're going to get approaching 0, right? You're going to get this y-intercept of 1, right? That's a 1, right? And I can put this here just to show you guys this. So this is 3 raised to the x, right? And you can see here what I'm talking about. Well, if it'll zoom in. Okay, so we get this y-intercept of 1, right? We see this exponential growth and it approaching 0. Okay. And then so the next question says write an explicit equation for x plus 2. So that's x plus 2 plugged into the graph. So this would be 3 raised to the x plus 2, right? So if we graph that, right, if we went over here and said this is x plus 2, right, we can see that it, well, actually, I don't want that. So keeps putting it down here on me. So let's go up here. Let's put parentheses plus 2, right? Close. So we can see here, what does it do? It moves it left 2, right? So we get this cross hit there at 9. So we get, again, what's happening here is it moves it left 2. So that's where your 1 point is, right? And you're going to get this same deal, but then up here is going to be at 9, right? So, so looking at that, right? Then it says now write an explicit equation for 9 times f of x. Well, that's just 9 times 3 to the x. Okay, so that's a vertical shift of 9, but we can already know that if this y-intercept goes from 1 to 9, and this is a vertical shift of 9, that this and this are going to look the same, right? So part D then says, what do you notice about these graphs? They're the same. So this horizontal shift of left 2 and this vertical stretch of 9 are actually the same transformation for exponentials. which is really, really neat, right? So then looking at 14, we have now a function of 3 times 4 to the x, right? And it wants to say, okay, same deal. Let's look at f of x plus 2. So this would be 3 times 4x plus 2, okay, equals, and we're going to set it equal to 16 times 3 times 4 to the x, right? So we just multiplied the thing by 16. So again, going through this is 3 times 4 to the x times 4 squared. Well, 4 squared is 16, right? So same deal here, right? So we already see we're going to end up getting the same thing. 16 times 3 times 4 to the x, right? So these are the same, right? So same transformations, right? Let's look at b. So same deal. 3 times 4 to the x minus 1 equals 1/4 times 3 times 4 to the x. So again, this would be 3 times 4 to the x times 4 to the negative 1. And then 4 to the negative 1 is 1/4, which again gets us this same deal. Okay, so 15 just explains this. As you saw in the previous problems, for an exponential function, a horizontal shift is equivalent to a vertical stretch, right? So just looking at this, helping to understand that, right? That those are the same, and that's how that works. Okay, so then let's look at 16, and let's kind of make this make sense, right? So j of x is 12 times 5 to the 2x plus 1 plus 7, right? So now we have this, can this exponential function be written in the form a times b to the x, right? And here's the deal. Like, we can clean this up all day, right? So 5 times 2 to the x times 5 to the first, right? Then we can change this to 5 squared to the x, right? Like, all that's multiplied. The problem is this plus 7 can't go away because it's a different order of operations. So when you have a addition or subtraction on the end, you can't then get rid of this to clean it up in that y equals a times b to the x form, right? Just because that number, there's no way that that's going to multiply into it. So yeah, so that's neat lesson as far as understanding that vertical transformations or vertical shift, stretch, excuse me, can be the same as a horizontal shift for an exponential. But still the same rules apply as transformations go to exponentials as they would to our other functions.